So it's great to finally be here. I've wanted to come to the Flatiron, the CCA, for a long time. And so we finally managed to make it work, and this is a wonderful place, and you've kept me busy all day. And it's nice to see so many friendly faces here. So as you may have noticed, you have some A, B, C, D cards in front of you, which you'll be asked to use shortly, and I'll explain the rules of the game. But before we start the game, I found it useful to give you kind of a broad overview. I noticed there are many experts in the circumgalactic medium here, but maybe you'd like to hear my short spiel on why I think the circumgalactic medium is important. And so what I'm showing you is this image, which perhaps some of you are sick of at this point, but Jason Tumlinson, Molly Peebles, and myself put this in our annual review article in 2017 as our kind of ultimate cartoon of the circumgalactic medium that's meant to illustrate that, you know, a galaxy lives a life of turmoil, of constant upheaval, where it balances, you know, infalling material with recycling material, and star formation is constantly pushing material then out of the galaxy. And this gas in the circumgalactic medium is playing an incredibly important role in galaxy evolution. But I really look forward to a day in which we can take this picture and just put a giant red X through it. I mean, it's almost certainly a very simplistic view of the circumgalactic medium, and one that doesn't capture all of the rich physics contained in this medium. But before we talk about the circumgalactic medium and the cosmic baryon cycle on large scales, I first want to focus on a much smaller human-sized scale. And so most of you here readily appreciate that your physical bodies are composed of atoms that were not fused for your exclusive use. Perhaps I think one of the most important illustrations of cycling on our own planet and recycling is the following analogy. And so if everybody just takes a deep breath in, hold it in, feel it in your lungs, and then let it out. And so the number of atoms in that single, there are more atoms in that single breathful of air than there are breathfuls of air in the entire Earth's atmosphere. I find that, you know, scaled argument incredibly compelling, because what that means is that breath of air you just drew in probably contains at least one atom in common with the first breath you ever drew as a human on planet Earth. And so just as the atoms on our own planet and the air are recycling through constant forms over the course of the Earth cycle and your own life cycle, so have they been cycling on an even larger galaxy-size scale. And so in that way, you might liken the circumgalactic medium as something like the galaxy's breath. And then finally, if you want the analogy to be even more explicit, perhaps you've seen this lovely t-shirt helpfully pointing out our location in the Milky Way spiral arm. But somewhere between 6 and 9 billion years ago, more than 80% of the atoms in your body were out here. And so I think that the circumgalactic medium has quite a lot to tell us about our cosmic origins. And so that leads me to the introduction of the game that we're going to play today. Okay, so I've designed a fully interactive colloquium in the spirit of old MS-DOS adventure games that will basically allow you to lead your own collective, unique exploration of the circumgalactic medium. So you're going to be asked to vote at various junctures in this talk, and using your A, B, C, D cards. This is an entirely democratic process, majority rules. And I'm just going to be counting in real time, and I'm pretty good at it. If it's a tie, I'll just pick what I want to talk about. Okay, so does anybody have any questions about the game, or you know how it works? It's fairly straightforward. Does everybody have cards? If you don't have cards, now's your time to run and grab a set of cards, and everybody has A, B, C, D options. Very important. We want everybody to be able to participate. Yes, thank you very much. This is the perfect time. There's somebody in the back, too, if you want to pass some back. All right. Here we are. We find ourselves orbiting a star called Sun on planet Earth, located in the Orion spiral arm of the Milky Way galaxy, and our mission is to find out how we got here. All right, more specifically, your body is composed of ancient star stuff expelled with supernova and or during stellar death throes, cycled through many timescales over billions of years on physical scales of megaparsecs, before it's used as raw material to form new stars and ultimately ends up on a planet and in your body. How? All right, so you're going to be presented with a number of options straight away. You have tools in order to figure out your cosmic origins. You're going to have to decide, would you like to use the Hubble Space Telescope, the Keck telescopes, the Gemini telescopes, or the Pleiades supercomputer?
You're asking yourself.
Yes.
Oh my gosh. See, this is probably the most D's I've ever seen the first time. I don't know if they beat A.
I want to hear about simulations.
Ah, interesting. Okay, I'm taking D. I'm sorry. Yeah, Brennan, you lose. D1.
D should be banned at the CCA.
Yeah.
All right, you chose the Pleiades supercomputer. The first time I've ever given this talk that's been chosen first. Congratulations. So now to continue on your mission, you're going to have to design a computer simulation optimized for a specific scientific goal. All of you are familiar with this. You have two choices. You can investigate black hole feedback with genetically modified galaxies, or you can use synthetic spectroscopy on simulations that include cosmic ray physics. All right, you chose A, but I think that you're directly driving a dagger through the heart of Irina, who is sitting here, who would have been highlighted and
We just had a whole group meeting.
All right, so you chose to investigate black hole feedback with genetically modified galaxies. And in this, we're having a little bit of a technical issue. I've got the rainbow spinning wheel of death here. Abort. Let's not abort, though. Let's see if that works. Let's see if I can get, okay. Whew. All right, so I'm going to be highlighting work that was done largely by my graduate student at the University of Washington. This is Nicole Sanchez here. She's also the lead singer of the Night Lunch Band. That's her pictured there singing. So she decided to lead an exploration of cosmological simulations run in Romulus 25. This is a 25 megaparsec cosmological volume, SPH simulation. And she also then genetically modified one particular galaxy 4 distinct times. And this genetic modification tool is a way of just slightly tweaking the initial conditions so that you kind of hold everything constant except for one parameter that you might tweak ever so slightly. And this has been pioneered by Andrew Ponson at UCL. So what Nicole did for this experiment to investigate the circumgalactic medium was she first chose 52 galaxies with a mass range that kind of is similar to that of the Milky Way galaxy, a stellar mass that goes from about 3 by 10 to the 9 to 3 by 10 to the 10. It's a little lower, I guess, than the stellar mass of the Milky Way. And then she chose one galaxy that she called Patient Zero. That's kind of a true Milky Way analog, and then genetically modified it. And I'll tell you a little bit more about those specific genetic modifications that she did on those galaxies. And so they're two experiments, but they're uniquely related to each other. And she was going to explore oxygen-6 in the circumgalactic medium in particular. And so what you can see here is actually a result from Tumlinson et al. 2011 and the COS Halos team. The galaxy data come from Werk et al. 2012. Many of you may be familiar with this plot, but I'll walk you through it. What you see on the x-axis is the projected distance from the galaxy in kiloparsecs. This is a sightline, a quasar sightline that pierces the galaxy at some distance. And then the column density along that sightline observed in the ionization state of oxygen-6. And what you see here are a division between star-forming galaxies and quiescent galaxies, where star-forming galaxies, as blue squares, tend to show an oxygen-6 column density between 10 to the 14.5 and 10 to the 15, fairly universally, whereas the red galaxies show somewhat lower column densities, or not at all. So there are a number of non-detections around red galaxies. And so one of the key results from this work is that the galaxy dichotomy, which presents as the kind of red and blue galaxy dichotomy in galaxy disks, also is manifested in the circumgalactic medium through oxygen-6 in particular. And so this has been a kind of interesting benchmark observations for a number of theorists to compare to. Nicole did just that, and so she took the 52 Romulus 25 galaxies that roughly span the same mass range as the points that are plotted here, and shows that yeah, she can roughly match the oxygen-6 column densities, but it doesn't seem like there's any bimodality that's really emerging here. The red galaxies have almost just as much O6, and this is a result that's been also reproduced in other cosmological simulations. Ben Oppenheimer found that, in fact, it might be more of a halo mass term. Okay, so she's not finding, at least in the simulations, that star formation is significantly affecting the column density of O6 in L-star galaxies. Okay, so that's fine. So now she's zooming in. She has these 4 galaxies that are slight modifications of this patient zero Milky Way analog. And so one of the reasons that she chose this patient zero galaxy is that it has an LMC type structure in its halo. And so one of the things that you can do in your genetic modification is slightly modify the original mass of that LMC type structure that is eventually going to merge with your Milky Way patient zero. And so you can tune the mass slightly upward or slightly downward. And that's what she's done in these 4 genetic modifications. 2 are tuned slightly more massive and 2 are tuned slightly less massive. And you find that, you know, all of them seem to lie along this oxygen-6 distribution. Well, that's nice too. So it's kind of a null result, but in general, she finds the same thing as Ben Oppenheimer did, that in fact the quantity of oxygen-6, which is the green square here, and this is just the oxygen fraction in different ionization states of oxygen from O1 to O8 here, that the quantity of oxygen-6 and oxygen-3 actually depends on the halo mass, and that you're actually maximizing oxygen-6 at lower masses. Okay. But she did do something else in her genetic modification, which is that she turned off black hole feedback. And so she ran the same genetic modifications on that same patient zero galaxy, except now she just turned off black hole feedback in her galaxies. And in the simulations, black hole feedback is implemented with some physics, special Tremel feedback, Michael Tremel's feedback model, if you're familiar with this. But it's kind of a generic, I think, Bondi-Hoyle kind of accretion, but it's a little bit more specialized. And what you can see is, though, when she's turned off black hole feedback, you get very, very low oxygen-6 column densities in the circumgalactic medium. And so clearly there's a distinction between the galaxies with black hole physics and without black hole physics in terms of their circumgalactic medium. And so one of the things that she actually discovered is that this is not a temperature effect. This is also not a density effect. It appears to be a metallicity effect. And so you can look at the metallicity profile of the gas in the circumgalactic medium, and what you find is actually that the black hole is taking the metal-enriched gas from the center of the galaxy and moving it directly into the circumgalactic medium, which ultimately results in elevated oxygen-6 column densities in the circumgalactic medium. And so this was her first paper and a very exciting result. And so we've now learned that a galaxy's mass likely influences the phase structure of the CGM, and that supermassive black hole feedback physics play an essential role in moving metals into the circumgalactic medium. Now we must, and so would we like to study galaxy metal retention using Andromeda as a laboratory, understand more about CGM observations with HST, or use another tool? Yes, question.
Before we move on in our adventure, can I ask a question about that?
Please.
Something very similar is actually seen with the Lyman alpha forest, where when you turn on and off black hole feedback, the column density of neutral hydrogen absorbers changes similarly. So would that fit with this metallicity argument as well?
Well, with Lyman alpha, right, that's...
I mean, you wouldn't necessarily need a different metallicity.
Right, because one of the things that we found is it's not actually moving a ton more material into the circumgalactic medium. It's the metals in particular that it seemed to be preferentially moving. So no, I don't think directly, but that's very interesting. So is this, what's the paper that I can look at?
There's several, but the first with the simulations was Gurvich.
Okay.
At all. But we can talk afterwards.
I would love to.
There's also a work on cluster scale where people do simulation with and without aging feedback.
Mm-hmm.
And if you include aging feedback, some of the finding actually shows that the metallicity is high and flat out the outskirts of clusters. and that's thought to be the early enrichment, where you do like eject the gas early on, then the gas kind of strips out. So that's one of the insights that people actually see these differences due to aging feedback in galaxy clusters as well.
That's great. That's wonderful. Thank you.
So does it mean that in one or the other case, then you're either on and off mass metal stimulation? Because it's a huge amount of metals that are being injected, like most of the ISM.
You're either on or off what, Nishan?
The mass metallicity relation. You're on the mass metallicity relation regardless. So I don't know exactly how that works. So this is the metallicity profile, but I think within the galaxy itself, maybe it's not changing things so dramatically or not enough to take it off the mass metallicity relation.
But given that there's a large reservoir and you go to third solar or something, then it means that it's as much as an ISM.
That's true.
So,
Yeah, that's a good point. I don't know. Yeah. All right. But now we have to vote. So Andromeda as a laboratory for galaxy metal retention, understanding more with the HST, or using another tool. Wow, everybody wants to go to Andromeda, which is wonderful. Except for Grace herself, who is sitting here. And so, but now I feel very fortunate that I get to highlight the work of Grace Telford, who's here, who was a graduate student at the University of Washington, who recently graduated and is now a postdoc at Rutgers and a visiting scholar at Flatiron. Okay, so you'll get to ask Grace more questions if you have any about this particular work. So Grace is tracking the cosmic baryon cycle using metals, because metals form inside of stars, of course, that predominantly live inside of galaxies. And so in this way, they act as tracer particles of material that has been in the stellar disk at some point. And what Grace did for this project was she used FAT, the pan-chromatic Hubble Andromeda Treasury, a multi-cycle HST program that mapped Andromeda in 6 different filters and resolved something like, I don't know, 6 million stars. Oh my gosh, auto update, no thank you. What is happening with my computer? All right. But in general, you can resolve the star formation history across the disk of Andromeda, which is very impressive. And so ultimately, this gives you, not only do you resolve the star formation history, but you can resolve something called the metal production history of Andromeda. And in particular, Grace focused on the metal retention fraction. And so this quantity can tell you what fraction of metals have stayed in the galaxy disk, and conversely, what fraction of metals have been lost from the galaxy disk. Because if you know the star formation history, you know the total number of stars that have formed, you have some estimate of the yields and the supernova rate, and so you can figure out the total number of metals produced, and then with measurements, you can go out and measure how many metals are actually present, and this tells you either how many metals are still in the galaxy or how many metals conversely have been lost, assuming that you're not losing metals once they're created. And in general, I think that that's probably a fine assumption. So this is just an example from FAT of the color magnitude diagrams that you can derive and that allow you ultimately to derive the resolved star formation histories and resolved metal enrichment history of Andromeda. And so from doing this in every single field of view of this HST FAT footprint, getting color magnitude diagrams, fitting isochrones, Ben Williams in 2012 derived a star formation history, or I guess in 2017, resolved a star formation history of Andromeda. So a couple things to note about this figure is that the early time, you know, you're in a very large bin there, right? You don't get very good time resolution at very early times, but you can see at later times too. The star formation rate of Andromeda fluctuates over cosmic time. And so what you're seeing is the star formation history, but of course Grace was able then to turn this into a metal production rate specifically. And there are a large number of uncertainties in calculating this metal production rate, and in particular in the type 2 supernova rate, the type 1a supernova rate, the AGB yields. You can see Grace meticulously tracked the uncertainties in each of these quantities, and you can see type 2 supernova dominate, but these contributions are not insignificant from the other components. Okay, so now we have a metal production rate, and so here is Grace's spatially and temporally resolved metal production history. The first bin is all just the same, but it's going to start changing. And what I love about this is you can start to see that the metals are produced in the spiral arms. You see the spiral structure kind of jump out. You see there's a lot of metals in the center of the galaxy that have been produced, where quite a bit of the star formation has taken place. And so then what you need to do is you can take an accurate census of metals present in the stars and the gas and the dust. And so Grace did this. And you get some metal profile. Most of the metals turn out to be in stars. Some of them are in dust in the galaxy and in the ISM as well. And again, she meticulously tracked the systematic uncertainty budget for each calculation. And so let's combine the two into a metal retention fraction for Andromeda. And you can see that metals must have been lost from the M31 disk. Now, while the uncertainties are large, they're completely dominated by the highest mass star that explodes as a type 2 supernova. Apparently, this is incredibly uncertain. And depending on what you assume for this mass, you can get huge uncertainties. Now, if you just choose Grace's favored model, the uncertainties from the rest of all of the assumptions lie in this blue band. But regardless of what you assume and the huge uncertainties, Andromeda's present metal content sits down here. And so immediately we learn that Andromeda must have lost a significant fraction of the metals that it produced over its life. And not only that, but you resolve where they're predominantly lost from. And so you find that the retention fraction of metals ranges between 13% and 93% in the Andromeda galaxy. So that's a large range, but some fraction of metals had to have been lost. And if you there's been a survey of the circumgalactic medium of Andromeda. This is called Amiga. They find that the cool CGM, at least linear, when they trace this cool low ionization state CGM of Andromeda through lines like silicon 4 and silicon 3, they don't really detect very much, so they put some upper limits on this. It's not totally it might be somewhat inconsistent with our data, which is if you assume that we have if M31 has all of its baryons, that is, in the dark matter halo, 17% of its mass is baryonic, then the metallicity that would be implied by the missing metal mass would be right where you might expect for other sorts of galaxies, 1/3. And what this might be saying is that the metal mass of Andromeda, at least, is not residing in the cool gas then. If you anticipate it's in the CGM, it might be in a much hotter phase. But I think one of the more interesting results from this work is that you can get a missing metal mass map from Andromeda. And so this is resolved here, and you find that most of the metals missing from Andromeda are missing from the central regions of Andromeda, which actually ties in very well with what I was saying before, although potentially star formation is more clustered in there too. So in general, now you do not have a choice. You've found a hole in my talk, but you're not going to find out what's driving the metals out because, well, maybe I implied that it was black holes, so we have to figure out where the metals go. So now you're going to use bright blue quasars at a redshift of 1. Actually, do you guys want to use another tool? That'll get you. All right, we're going to abort the mission. No, all right. Whew. See, this is like, okay, what tool would you like to use? I like to give you choices. No, Chris. C is definitely not winning, Drummond. I'm sorry. I think if you have an A or a B, can you just keep the A's and B's up? It's going to be easier for me to count. Sorry, guys. I think you're getting A. You chose A, but you get to choose again what you're going to point it at. So, would you like to point the Hubble Space Telescope at bright blue stars in the Milky Way galaxy halo? Would you like to point it at bright blue quasars at redshift 1? Probably don't want to point it at Andromeda again since you just heard about that, but you can also point at O stars in M33. Thank you for not choosing C again, everybody. All right, A. You chose bright blue stars in the Milky Way galaxy halo. All right, so we've been talking a little bit about gas hundreds of kiloparsecs from the galaxy, at least what we were tracing with Nicole's study. and stuff inside of the galaxy. But between 1 and 10 kiloparsecs from the galaxy disk is a region known as the disk-halo interface. And this is where the true action of accretion and outflow are occurring. This is a kind of cartoon of what's envisioned as the galactic fountain. I don't hold this picture in my head necessarily, but it's one of the ones that everybody uses for the galactic fountain. I should take one of the pictures from Drummond's simulation or Changu Kim's Tigris simulations. But in general, material is ejected from the galaxy, which we've learned, from Andromeda. It cycles, close to, in this disk-halo interface region, goes out and comes back in. And the phases in which it does so are potentially multi-phase. The rates at which it does so are potentially governed by rotation, the ejection speed. All right, but before we begin, I have to give you a little bit of context for the observations, which is that detailed calculations based on hydrodynamical simulations are indicating that anywhere between 60 and 80% of the photons emitted and absorbed by diffuse galactic halo interface gas are UV photons. So at low redshifts, the study of the circumgalactic medium is inherently UV science. And that's really the main point I want to make with this plot. And so this is a plot I would like to show you, just explaining some of the ions that we use as tracers in the ultraviolet. This is a plot that I call the fake phase plot that I was forced to make. This is in the annual review article with Jason Tomlinson and Molly Peebles. And they insisted I make this. I dragged my feet, but I made it. And everybody says it's very useful, but I'll just give you my caveats for why I didn't want to make it, which is that the x-axis represents the equilibrium density that any of these given ionization states of metal lines would have if they're in pure photoionization and thermal equilibrium. The y-axis, on the other hand, indicates the equilibrium temperature that any of these ions would have if they're in pure collisional ionization equilibrium, right? So you're getting temperature from collisional ionization equilibrium, density from photoionization equilibrium. It's a little disparate. However, it's actually not a totally insane physical picture. So it's fine as an approximation to hold in your head, but there is a caveat. And look at these densities have a huge range, necessarily so. So that's one of the things that you need to derive from detailed modeling and that we're still not sure about how to model. But in general, some of the ions, here's our friend O6 who lives up here at an equilibrium temperature of about 10 to the 5.5 Kelvin. This is the peak of the cooling curve. It lives at very low densities, whereas things like silicon-4 are a little bit lower temperature material and higher densities. And so these are the kinds of ions that we'll be talking about. And generally, because the circumgalactic medium is inherently UV science, the new UV instrument that was installed on the Hubble Space Telescope in 2009 during the resurfacing mission by John Grunsfeld and Andy Fustal really just was a total game changer for CGM science. This spectrograph is over 30 times more sensitive to UV photons than previous generation UV spectrographs, and the field of circumgalactic medium science really just opened up completely. All right. And so for this work, I'd like to tell you about work that I've been doing with UW graduate student Hannah Bish. And this is work at this Milky Way disk halo interface where we're pointing the Hubble Space Telescope at bright blue stars in the Milky Way halo. And these are the stars that we have to work with. These are blue horizontal branch stars. They're cataloged by Segway, actually, for totally different reasons. The catalog was first published by Zue et al. 2011. In fact, they're, I think, often used to make dynamical mass measurements of the Milky Way halo. These are halo stars that actually extend up to like 50 kiloparsecs into the halo. The brightest ones that you can point Hubble Space Telescope at and get good high-resolution cost spectra with are within about 15 kiloparsecs. And you can see here our sample of stars. So the experiment that Hannah and I did was at very high galactic latitudes, tracing a very small region of space and sampling it very, very densely. And we did this with both Keck and COS. The COS data are shown in yellow. And you can see it's just kind of a line of stars going from about 3 kiloparsecs to about 13 kiloparsecs into the halo. And we originally sold this as a Cycle 23 and Cycle 25 COS program as tracing gas physics as a function of height from the Milky Way disk. As you'll find, that's not ultimately what I'm going to tell you about. It's uninteresting. There's no nothing as a function of height. Everything is within 3 kiloparsecs that we see. And so in general, you take a high resolution spectrum and it looks something like this. Now theorists will be like, what is that? There's a lot of noise. Yes, but there's some absorption lines in there. And the great thing about blue horizontal branch stars, and one of the reasons to use them, is that not only are they UV bright, but they don't have a lot of metals in them. They aren't doing a lot of crazy, they don't have crazy winds. And so they make a really nice continuum against which to measure absorption features definitively. And so that's all this is meant. It's just like, it's not, this is without any kind of continuum subtraction or anything. It's just this beautiful spectrum upon which you can see, you know, absorption lines from gas. And one of the things I quickly, you know, realized and didn't appreciate totally fully, although I probably should have, is that these lines of sight kind of skirt the edge of a well-known structure as known as an intermediate velocity cloud, and it's a large intermediate velocity cloud toward the north galactic pole. And they're kind of on the edge of that structure, but you can see that there's detected H1 21 centimeter emission in this kind of intermediate, what's called intermediate velocity range, where this is normalized to the local standard of rest velocity, where the Milky Way is at 0 kilometers per second. All right, and so another thing to just remember as I talk about this, the cost aperture, of course, is 2 arc seconds, whereas an H1 beam size to make these emission maps is 10.8 arc minutes, which corresponds to a size of about 10 parsecs at a distance of 3 kiloparsecs. Something to keep in mind. Again, this is just showing you well-known intermediate velocity clouds. So this IV arch is the one to note here. Like I said, we're just on the edge of this IV arch. Those are our 7 blue horizontal branch star positions. All right, and so here are some cost spectra. And one of the things I think that you can tell immediately is if you look at carbon-4 and silicon-4. So now we're in velocity space here, and you know the thing about spectra is you collapse the 3rd dimension along your line of sight into this velocity space, and so we have to think in terms of the Milky Way. So these are now all normalized to the local standard of rest. We've got Milky Way highlighted in green. This is what I associate with Milky Way absorption of the ISM. The stellar, you know, the star has its own radial velocity. They were chosen to lie at large radial velocity so that if there were any absorption, we'd be able to separate it. You don't really see anything from the star and silicon-4 and carbon-4, but you do in like iron-2 and in silicon-2 here. And so we didn't necessarily expect that. I guess stellar evolution people did. They said that they were metal-free, which is clearly a lie. And so, but what you can see here is that the carbon-4 and the silicon-4 look very different from the iron-2 and the silicon-2. And that's really, you know, the main point of this. Is you can see the bulk of the absorption in iron-2 and silicon-2 are fairly coincident with the local standard of rest of the Milky Way, indicating that you're going through ISM. Your line of sight pierces the ISM, and then anything at the disk halo interface. Whereas the silicon-4 and carbon-4 are offset. And one of the things we did was we tried to fit, you know, kind of 2 components for each line. We demanded a Milky Way component for silicon-4 and carbon-4, and we fit just an intermediate velocity component. But what we're going to be focused on in this study is the intermediate velocity component. That is the stuff that's not Milky Way and the stuff that's not stellar. Okay, and so we can fit that absorption and understand its column density and its velocity centroids, and try to understand something about the disk halo interface in the process. And so what we find is, well, first of all, when we plot things as a function of height from the disk, which is this z here of the star, and of course the star just gives you an upper limit to the distance that the absorption could have, right? Because it's your bright background source. So all of the absorption has to be in front of it. And so you would think that if there's material, more material above, you know, 3 kiloparsecs up to 12 kiloparsecs, that as you go up in height, you would get more and more material, but we're finding that's not true at all. So as I mentioned, tracing gas physics as a function of height, that's not happening. Okay, so what else can we do with these data? Well, one of the things, maybe, I don't know, you're theorists, but one of the things that observers might notice is, okay, so this is not demanded even remotely, but if you look at the carbon-4 in orange and the silicon-4 in purple, these points here, like I didn't demand that they be the same, but if you look at the way that they're like fluctuating with each other and their different positions, they're like mapping each other perfectly well. Not so much with the iron-2 and the, what is the other one there, calcium-2. All right, so let's look at the carbon-4 and the silicon-4 a little bit more. Again, like I said, they're varying, close to each other. If we try to correlate that with the H1 column density, they do kind of correlate generally with the total H1 column density observed in emission, which is not necessarily what you would expect. You would expect something like calcium-2, which has this low ionization potential, less than about 10 eV, to correlate with neutral material. But you don't really see that at all. Now, this could be a total product of the different spatial scales. But at the same time, finding the correlation between carbon-4 and silicon-4 in H1 is kind of interesting. H1 might be tracing kind of larger structures. This is starting to tell you what might be actually interesting to examine with these data is a coherence length in kind of the XY plane. And so that's what we started to do, because one of the things that's highly uncertain in the disk-halo interface or the circumgalactic medium is the structure. What are the typical sizes of these clouds, clouds that are swept up in the galactic fountain or that are ultimately accreting? And so I made these plots. They're not as instructive, but one of the things that you can start to see is that in carbon-4 and silicon-4, you can see a clear correlation in the XY plane with each other, whereas, again, calcium-2, iron-2 are just a total mess, all right? So what do we learn from this? Well, one of the things you can do is do this kind of pairwise separation. So there are 7 pairs, right? And you can pair each one of them. So there's 21 unique pairs of the 7 sites. There's 7 sight lines. There's 21 unique pairs of each one paired, okay? And then you can take the difference in column density for each of these ions, for each of the pairs, versus the pair angular separation. And what you see, and this corresponds to 20 degrees, corresponds to 1 kiloparsec at a distance of 3 kiloparsecs. So assuming all of this stuff is within 3 kiloparsecs, the nearest blue horizontal branch star, you can see this dramatic correlation, and this is highly statistically significant. That is, the carbon-4 and silicon-4 and H1 are actually correlated across very large angular scales in our data in this kind of XY plane. The iron-2 and the calcium-2 are not at all. Like, you can even see the range here is much, much higher, right? It goes all the way up to 1.2 dex in this column density space. And so one of the things I think to take away from this figure, and one of the main takeaways, and now this is from Werk et al. 2019, it's on the archive, it was just accepted, I'm going to post a revised version soon, but high ions in H1 are tracing coherent kiloparsec scale structures. I think that this is telling you this directly. Other people have made assertions kind of more indirectly from covering fraction arguments, but I think what we're seeing here is directly an argument for kiloparsec scale structures in this kind of intermediate ionization state gas. Whereas for iron-2 and calcium-2, you're seeing this total scatter. They don't also trace H1, and that's one of the key points here is that the H1 beam size, it corresponds to about 10 parsecs at 3 kiloparsecs. So they're possibly tracing structures smaller than 10 parsecs. Now, we did this a little bit better with Keck, but you're probably not going to get to hear about that. But I would say anywhere between 10 parsecs and 500 parsecs are kind of the size scales of this low ionization material. And the other thing I did was some ionization modeling. And this is because what I was really obsessed with and what I pointed out earlier is that the silicon-4 and the carbon-4 are varying with each other very much so that their column density ratio is basically constant. And it's this constant value of about -0.7 in log space, all right? It doesn't vary very much. These are a full spread of our measurements, right? The median value of like 0.69 has very, very little error on it, okay? So this value actually turns out to be really interesting and really constraining. And so this value is constrained. Of course, the fraction of carbon in carbon-4 will depend on the metallicity of the material, the metallicity that you assume for the material. And there's another constraint you can use to actually constrain the density, the amount of carbon in carbon-4, but you can use the pulsar dispersion measure. So there are also pulsars in the halo of the Milky Way, and this gives you a direct constraint on the dispersion measure, which is like an electron column density through a plasma. I won't tell you all the physics of that, but using those constraints and then additional metallicity constraints from some intermediate velocity cloud measurements, you're immediately in this regime here where basically, 25% of your carbon has to be in carbon-4, but then you're at odds here. And so one of the things that comes out of this, these kind of disparate solutions that I'm highlighting in blue and red from the pulsar dispersion measurements and the independent metallicity constraints, is that if you want the gas to be metal enriched, which it almost certainly should be metal enriched, then silicon-4 has to be depleted relative to carbon-4. That is, you have to be, for some reason, your ratio is way down here telling you, oh, maybe there's very low metallicity gas, but actually it should be closer to this because silicon-4 is being depleted onto dust. And that's not actually crazy. All right, so there are some studies that tell you that in the warm ionized medium of the Milky Way, there might be some significant amount of dust affecting this medium. And so what I think that this ratio is actually telling us is that WIM gas is pretty dusty, on the order of what it is in damp Lyman alpha systems outside of the Milky Way. And this is not contingent on what you assume for the H1 column density, by the way. I just want to mention. That's what that other plots. But also, you could say, well, what if silicon-4 and carbon-4 are collisionally ionized? I actually have other arguments that show maybe they're probably not. But one of the constraints you get from that, that's fine. This ratio, again, is here at -0.7. It lies along the CIE curve when carbon-4 is 20% of all the total carbon. And so that limits you, though. Like, that means that your metallicity of the gas has to be at least 1/3 solar. And why that's interesting is that if you're going to ask that the gas be collisionally ionized, it actually comes from a very different origin, right? Like, it's probably cooling out of a hot corona. And as far as I know, there are no independent constraints on the hot corona of the Milky Way. So if you favor a model in which carbon-4 and silicon-4 are collisionally ionized, then you're demanding that the hot corona of the Milky Way be about 1/3 solar metallicity. And then finally, this was something new that I added to the paper, which is about to be reposted to the archive. The referee asked me to determine the mass accretion rate, and in particular, we can actually do that very well, determining an aerial mass accretion rate, assuming that these structures are about 1 kiloparsec in size, with our constraints on the fraction of carbon and carbon-4, constraints on the metallicity, you could get a range. In general, we know an accretion velocity as well. These are straight up, right? Their accretion velocities moving toward the galaxy within 3 kiloparsecs are about -45 kilometers per second. If all of this material gets accreted onto the Milky Way, its aerial mass infall rate is about 0.0008 solar masses per kiloparsec squared per year. That might seem low, but that's approximately the aerial star formation rate of the Milky Way galaxy. Now this is a little bit lower than other estimates from halo stars in the Milky Way, aerial mass accretion rates of ionized material, but this is the one that's closest to the disk, which I also think is fairly interesting. In general, this corresponds to a mass infall rate of something closer to like 0.1 solar masses per year. So it's a little on the low side, but it's just in this ionized carbon-4 phase. And so I think we're done. You don't get to choose, unfortunately. Keck would have been nice, but we're going to abort the mission, and I'm going to thank you for playing the Colossal Galaxy Adventure and learning about your cosmic origins.
Any questions for Jess? Any more questions for Jess? Sorry?
So the last number for the infall rate would be the infall rate of total gas at that temperature?
Yeah. I mean, the thing is, if you're imagining that it's photoionized material at about 10 to the 4 Kelvin, these are these kind of larger, but it's like a larger scale, highly ionized structure, then it's a different density from the kind of cool clumps. But yeah, it's some characteristic density. If you're imagining it's collisionally ionized, it's at like 10 to the 5 Kelvin. But yeah, so gas in that particular phase that's traced by silicon-4 and carbon-4.
So going back to this metallicity effective to HGN feedback, I agree that the HGN could be important for like significantly mixing and getting the metals out. But you also have observations in sort of red and dead galaxies that metallicity is low.
Do we?
Do you? Or like I saw
No.
non-star forming galaxy. Did you not have an oxygen 6 that's very large?
Oxygen 6 is a little lower.
Oxygen 6 is low.
Then the H1 is present in spades, and also the low ions, so the lower ionization state material is present. And those metallicities are constrained, and they're just they're like half solar to solar. So yeah, they're quite metal enriched. Yeah, I didn't show that, unfortunately. I didn't talk about quasars, but yeah.
But do you actually have a simulation that reproduced oxygen 6 column densities for non-star forming galaxies? That's you see like most of the
In fact, the simulations don't get the oxygen-6 column densities right generally. So they did in Romulus 25, but there might be some issues because there's no metal line cooling, which we discussed in Nicole's paper. But simulations are typically like 0.3 dex lower than the oxygen-6 column densities, although recent work indicates maybe cosmic rays can help drive up oxygen-6 column densities. But the blue-red dichotomy hasn't been reproduced by the simulations, at least in terms of if you hold halo mass constant. But the red galaxies and cos halos do have a slightly higher set halo mass, so it could be explained by it. I don't think a mass effect is ruled out.
When we decided to point at Andromeda, you talked about how we can go and separately work out or observe the present-day metal abundances and then the metal the history of metal production. And I was just wondering if you could talk more about how we infer the past metal production.
Yeah, okay, so this was a lot of work done by Grace, and so Grace is your go-to person, but generally what she had to do was, assume a number. So once you get a color magnitude diagram, you figure out how many stars formed, when they formed. You have to assume things like an initial mass function, and then you have to assume yield rates. You have to assume mass bounds, and so this is where all of these uncertainties come from. And then how metals are produced are predominantly type 2 supernova, type 1a supernova, and AGB stellar evolutionary phases. And so cataloging how all of those are done, is an extremely computationally intensive process that I'm sure Grace can talk a little bit more about at some point if you'd like to ask her.
Great, thank you.
Yeah.
Rachel, you want to go?
Yeah, this is back to black holes. So Ina Choi has done work with simulations that include black hole feedback that's implemented in rather a different way. So it's from radiation pressure from the broadline region of a radially efficient accreting black hole. And she finds a similar effect that the metals get out more. So the gas density is depleted because a lot of gas is removed, but the metals get out. And this is unpublished work, but she can make these sort of movies as the black hole evolves. Then the oxygen-6 agrees with the observations, and then it just dives down when the black hole switches on.
Whoa.
So it may be the way that the black hole feedback is implemented that's really needed to get this
Yes.
bimodality. She does get this very strong bimodality, and it's clearly very closely connected to the duty cycle of the accreting black hole.
That is fascinating. Yeah, one of the things Nicole is doing right now is she's tracing metal fluxes as a function of time in terms of the black hole growth history, and so it'll be very interesting to compare to these models, I think. Yeah. Mary, you had a question.
Yeah, I'm wondering about your argument with the H1 versus calcium and such. Is that you're making the argument of scales, right? But I'm still not quite getting why you see that same gradient as the silicon-4.
I know. Well, so I think, okay, so let me, gosh, I have like a million slides here to actually go back to.
Yeah, I was going to have you go back, and I'm like, but how did she go back?
No, I can go back. Hold on. It's actually, if we just play the game again, I can get there easier. Hold on a second. All right, we got to use the Hubble Space Telescope. Sorry, we got to use bright blue stars. All right, there. All right.
So is this PowerPoint?
This
allows
is,
you to do this?
I know, it's hyperlinks. It's horrible technology, but. Okay, so, right, so the silicon-4 and the carbon-4 are correlating with the H1 column density roughly. And so if I go back to the H1 map here, you can kind of see that the H1 does have this level of coherence, and especially in the more diffuse component on large areal scales. And so that's kind of what I think what's driving this general correlation is that the very, very diffuse lower column density H1, which is, we're not over any of these smaller clumps here, is what's driving this generic correlation, right? So if you just assume that the gas has kind of a regular metallicity and that is this diffuse structure, that the silicon-4 and carbon-4 are generally tracing it, whereas I would argue that the calcium-2 and iron-2 are probably in very, very small clumps that are not being resolved, basically, is what the argument is. Just because there's no reason that iron 2 and calcium 2 should be tracing neutral gas better than silicon 4 and carbon 4. But if you're just assuming that they're kind of broadly tracing this diffuse component, whereas if the H1 is really clumpy, which I know that you've done work on this, like when you go to smaller and smaller scales, you resolve these like super small clumps, right?
I don't think there's evidence to support that when you compare the calcium and the H1, the absorption ionization, I thought they tracked, right?
No, the calcium and the H1 definitely don't.
Right.
So,
no, not in your observation.
Oh.
I'm thinking previous studies, I thought. But yeah, that's really interesting.
Yeah, I know. I found that actually very puzzling too. And I mean, maybe if we had like more data points over a larger region of the sky, you might find that. But for these, we're not.
All right, I'll take maybe the final one. So I'm really intrigued by this silicon depletion relative to carbon, and so much of the photoionization modeling assumes solar abundance patterns.
Absolutely
And
right.
you sort of taught me about this nitrogen 5 problem. And I'm wondering, and many people have brought up that maybe the solar abundance pattern is wrong, is a poor assumption. I was wondering, how much do you think we need to worry about this? This is in the disk halo interface, but also maybe out in the halo as well.
Yeah, I think we might need to worry about it. I don't know for sure. So you're right, this is within 3 kiloparsecs. So if you imagine a fountain, like there's a lot of dust in the disk of the galaxy that could, get lifted out and be kind of, entrained, to use a nice buzzword. Whereas, in the farther outer parts of the galaxy, I can't imagine how dust survives, way far out there in the presence of this extragalactic UV background, but it's not outside of, the realm of possibility, in which case, you have to worry about this a lot. And I will say not only dust, but non-solar ratios of the elements. Of course there's non-solar, right? Like why, you assume that for simplicity because you have no other choice when you're doing this modeling. But what I would love to do is, some study of general depletions. But what you need is a lot of time, very high signal to noise data with UV spectrographs that go far into the near UV that cover, a broad range of low ionization state transitions. I mean, I could write that proposal, but I doubt they would ever give me time for that. But yes, I think that this is the future, and I think in particular, I would love to measure different ratios of elements, specifically nitrogen to oxygen, I think would be a really good one. But if you look at like alpha elements present, you could constrain what types of feedback are happening. I mean, this is great. I think that it's really hard, though. It's really hard to do.
Some of the data might exist to look at this. I mean, we know the intermediate velocity clouds are dusty. You can detect them directly, but do you think some of the archival data could actually be used?
Maybe. It's something I've been meaning to check out. I think you would need very high signal to noise, and I would love it if it covered like zinc. And like these are very like near UV lines, but maybe for the interface you could do this and actually constrain the dust abundance.
All right, well, let's thank Jess again and then go get some wine.